And we will quantify this convergence by applying Chebyshev's inequality to the random variable sample mean. Okay, we know the mean of the sample mean, it's mu. So we can write the probability that the sample mean as a random variable is farther away from the mean mu for more than an amount of epsilon, where epsilon is a positive quantity, is upper bounded by the variance of this random variable divided by square of this quantity. This is Chebyshev's inequality. It's nothing new. Okay? And if you take the complement of this event here, okay, meaning the sample mean is within epsilon of the true mean. Now that is greater than or equal to 1 minus the variance of sample mean divided by epsilon squared. But the variance of sample mean, as we have seen before, is equal to the variance of x divided by n. So this is 1 minus the variance of x divided by n times epsilon squared. And if you take the limit as n goes to infinity, again, assuming that the variance of x is finite, this term will go to 0. And what you are left is, at the limit, the probability that the sample mean is within epsilon of the true mean, okay, for arbitrarily small epsilon, it's as long as it is positive, you can make it arbitrarily small, but the probability of this event at the limit as n goes to infinity is 1. Okay, so we say that when you have such a limit, the random variable m sub n converges in probability to mu. Okay, that's the term we use uh, in such cases where m sub n converges to well, in general, another random variable, but it's a deterministic value here. Uh, what does this expression mean? M sub n converges in probability to mu. That says that the probability of an unusual outcome, unusual in the sense that it doesn't converge to the, the mean mu. The probability of such outcomes becomes smaller and smaller as n gets larger. Okay? This is called convergence in probability. And this result, okay, this we call the weak law of large numbers. Large number here refers to the number of samples, not the value of m sub n itself. Okay, so this is the weak law of large numbers, and it states that the sample mean converges in probability to the true mean. In fact, we have a stronger result, which is called the strong law of large numbers, and it says that not the probability of being in the vicinity of the mu, but when you take the limit of the sample mean itself, okay, you just look at the sequence of the values of random variable m sub n, and at the limit, you evaluate the probability that m sub n actually becomes mu. And the strong law of large numbers state that this probability is 1. Okay, we call this almost sure convergence. Almost sure means the probability is 1. If you remember the discussion from continuous distributions, an event having a probability of 1 is not a certain event. There might be outcomes uh, that doesn't fit to this event, but they have probability 0. So that's what we have here. We say that sample mean converges almost surely to the true mean value mu. And what does that mean? The probability of outcomes that does not converge to mu is 0. So there might be some outcomes where the sample mean doesn't converge to mu, but the probability of observing such an outcome is 0. Okay? And why do we call the previous one the weak law and this one the strong law? So the strong law is strong in the sense that almost surely convergence implies convergence in probability. Okay, so if you have this, the previous expression follows from this expression. Okay, so this is the stronger result in that sense. I'm not giving the proof of this, it's a little bit elaborate, but you can find it in some textbooks. If you are really interested, for instance, Sheldon Ross, you can look at the a first course in probability book by Sheldon Ross for the proof of this. But as I said, the strong law of large numbers is strong in the sense that it implies the weak law of large numbers. Okay? And what is the significance of laws of large numbers? The strong law of large numbers enables us to use repeated experiments to estimate probabilities of events. As I said, for instance, you have a die which potentially may not be fair, and you do not know the probabilities of the outcomes. What you do is you just repeatedly throw it and record the outcomes. As the number of trials grow, okay, the probability of each event, each outcome will at the limit approach or converge to the true probability. So essentially we can say that the strong law of large numbers is the reason simulations work. Okay, this is a very key point. So to estimate the probability of an event, you just repeatedly perform the random experiment, but in an independent way. Okay, and therefore you can compute this probability estimate as number of experiments in which event A occurs divided by the number of trials. And we know by the strong law of large numbers that this estimate at the limit will converge to the true probability of event A almost surely. Okay, so you see, the strong law of large numbers tells us that there will be convergence, and the weak law of large numbers actually give us an idea about the rate of convergence, right? Because it's uh, based on Chebyshev's inequality, so that we can quantify the number of experiments to perform, and we can decide on the sufficient number of experiments so that we have a certain level of precision.